Hello everybody and welcome to another lecture video with Professor Algara. This is the second part of chapter 17. As I announced last week, I was going to post it a week after last Sunday. We'll be developing 17.4 and 17.5. I intentionally left the easiest part of the chapter for this video, so if you have any trouble understanding what we are about to cover, then go back into the previous video so you can be up to date with everything because you really need, this content or the previous content to understand what we're about to cover. All right, so we'll basically develop equations of motion when we have rotation about a fixed axis. When a rigid body rotates about a fixed axis perpendicular to the plane of the body at point O, the body's center of gravity G move in a circular path with a radius RG. Right here, just concentrate on this picture. You have a solid body and you have something or an axis that is coming through, through the screen and it's passing right through G. And when that happens and this is rotating in this direction, then you will have, G moving along with that, okay? Because that G is the center mass. The acceleration of point G can be represented in a tangential and normal component, very similar to what we've been doing until now. And the difference now is that we are having a rotational movement, and therefore the tangential and normal accelerations they need to be calculated in terms of angular acceleration and angular velocity. Okay, and this is just kind of what we have done in the past, and it's very important to say this because now, since the body experiences an angular acceleration, its inertia creates a moment of magnitude, or the torque that the moment of inertia is causing to the object. And then for that, we can now further develop the scalar equations of motion that we've had in the past in, sum of forces in the normal direction and sum of forces in the tangential direction. Both of them equals to the mass times acceleration in the normal direction and mass times acceleration in the tangential direction. And as I told you, the normal and the tangential acceleration equations, they will be written in terms of the angular acceleration and velocity. And finally, the third equation will be the sum of moment, about G, about the center of mass, that will be equals to the moment of inertia times angular acceleration, or the torque that the mass moment of inertia is causing to this object. It's very important for us to remember that the sum of moment around G, which is the center mass, can be replaced by the moment summation about an arbitrary point. And if that's the case, like this one, for example, if you take a look at this drawing, we usually do sum of moment about G so we can, get rid of some unknowns, but we can also do sum of moment about an arbitrary axis that is parallel to the point in G. And remember that those axes are coming out of the screen. When that happens, the only thing that we need to do is to make sure that we use the parallel axis theorem, in which we will just add, the distance between each one of the axes times the mass. And that's coming from the parallel axis theorem, as you know. And what we have to know is that now that term IG plus M, the distance squared times alpha, it will be now written by replacing this I whole thing by IO, which is the moment of inertia around O, multiplied by alpha, and those together, remember that's the torque that this is causing. And at the end, if we want to rewrite all of the equations, that's what we'll get. And these equations, those are what we need to solve the exercises. And now let's establish a procedure for analysis. Problems involving the kinetics of a rigid body rotating about a fixed axis can be solved using the following process. First of all, establish an inertial coordinate system and specify the sign and direction for normal and tangential components for acceleration. Then draw the free body diagram accounting for all external forces and couples, the moments. Show the resulting inertia forces and couple typically on a separate kinematic diagram, okay? Compute the mass moment of inertia, whether it's IG or IO, and that will depends on where you're doing your moment. Then write the three equations of motions and, identify the unknowns and solve for the unknowns. Okay, just solve your system of equations. And finally, just use kinematics if there's more than three unknowns, since the equation of motion allow for only three unknowns. Sum of forces in the x, sum of forces in the normal, tangential, and the sum of moments as well. And as always, let's just do solve an exercise so we can see a small application of what we have studied. A rod with a mass of 20 kilograms is rotating 5 radians per second at the distance shown. A moment of 60 newtons per meters is applied to the rod. We need to find the angular acceleration alpha in the reaction at pin O when the rod is in its horizontal position. So what we'll do, or the plan that is given, since the mass center move in a circular radius of 1.5, its acceleration has a normal component towards O and a tangential component acting downward because it's tangent to the path, as you know. We just need to apply the problem solving procedure. So first of all, we have the free body diagram along with a kinetic diagram. As you can see, the reactions at point O, when you remove the pin, then you will have the reactions instead, and then you have G because this is a rod, then G will be in the center of that rod, and then that will be equals to the tangential and normal components of acceleration times the mass based on everything that we had. So what we'll do, we'll go with a given, obviously, right? Or let's put it right here, given. And we were given with the mass, which is 20 kilograms, right? And then we also have omega, or angular velocity, which is 5 radians per second. And then we're also given with a couple moment, let's call that MC, equals to 60 newtons per meter. And it seems to me that the best way to start with this would be a sum of forces in the normal direction equals to mass times normal acceleration, or equals to mass r, which is the distance, or rg, let's call that, omega to the square. Okay, and then let's just give the direction. For me, this will be positive. If I do that, it's very simple. Minus on, because that's the direction, and that's my positive, equals 20 that multiply 1.5 times 5 to the square. I'm just plugging into the values, and therefore on will be equals to minus 750 newtons, or 750 going into that direction, which is opposite to what I have. And don't forget your units, 750 newtons. So now I need to do sum of forces in the tangential direction equals mass and the tangential component of the acceleration, and I will say that it's positive going downward. If I do this, then I should get, oh no, but this is also equals to mass Rg times alpha, right? And if I do that, I will get, minus OT plus 20 that multiplies 9.81, because we're talking about forces as a weight, and this is equals to 20 that multiplies 1.5, and then alpha. I'm just plugging into the values, and I will call this my first equation. So now I need to do sum of moment about O, so I can get rid of those two, OT and ON, which is what I'm looking for. So this will be equals to IO alpha. And this is, a good example, because now we need to calculate how do we do to calculate IO, because, as you know, the tables, or the mass moment of inertia for tables, they give us a value of how to calculate IG, which is at the center mass, but we're doing moment right here. So what we need to do is to find IO, and I took the liberty to remind you of the inertia, the mass moment of inertia when G is right in the center. What we need to do is just add to that the parallel theorem method. And then once we have that, it's super simple. So I will just go ahead and calculate IO. And IO for me will be IG, right, plus mass times the distance to the square between the two axes. When I do this, I know that IG is ml squared divided by 12, and this is plus 1.5 to the square that multiplies 20, which is the mass. And if I keep solving this, I will get that this whole thing I just plug into the values. Let's do this very quickly. So this is 20, then multiply the length, which is 3 to the square, divided by 12, plus 1.5 to the square, multiplied by 20. So when I do this, I know that IO it's equals to 60, right? And then what I need to do is that sum of moments about O will be equals to IO times alpha. So sum of moment about O will be equals to 60 alpha. And I just need to do the sum of moment and start doing the equation. So at first I have, and for me this is positive, that's the direction. So I will have minus 60, that's a negative moment, that's a couple, and then minus 20, which is the weight that multiplies 9.81 and the distance, which is 1.5, this is equals to 60 alpha. And all I have to do is to solve for alpha, and I will get that alpha it's equals to 5.9 radians per second square, and I just have to take this into 1, the equation that we were solving before, and with that we will get that the tangential component of O it's equals to 19 newtons. And with that, I just solved the problem. It's very important for us to know from this exercise that the only complex thing right here was just the thing to realize that the mass moment of inertia was actually applied at another axis different from the mass center. And if that's the case, you just have to use the parallel theorem method and you will be fine. All right. And now we'll be talking about the equations of motion when we have the case of general plane motion. When a rigid body is subjected to external forces and coupled moments, it can undergo both translational motion and rotational motion. This combination is called general plane motion, and we have done so many exercises with this. But now what we need to do is to start solving these exercises in x and y components, but not only that, but also adding the sum of moment around the center of mass. And the equations can be written, in terms of x, y, and o. As you know, we can develop these equations just as we've been doing. And it's very important for us to remember that we usually do sum of moment about the center of mass, but we can do sum of moment about an arbitrary point P. And if that's the case, we have to remember that IG will change for IO, and then we will have to add mass times the distance to the square. Just keep that in mind. If you are doing sum of moment at G, you're maybe simplifying the equation, but some cases you will have the possibility in which we need to do sum of moment around an arbitrary P that is parallel to the axis of the center of mass. So there is a specific case, right, when analyzing the rolling motion of wheels, and this is very specific. It might not be known if the body rolls without slipping or if it slips as it rolls. We don't know that. So for example, consider a disc with a mass m and a radius r, as you can see right here. The three equations of motion will be applied as if you do sum of moment in the x direction, you have p minus f equals to the mass times the acceleration of the center of mass. Then in the y direction, we have the same thing, but now we have mg, which is the weight okay? And then we have the sum of moment about g, about the center of mass, and that will be equals to ig times alpha. What we need to know right here is that we have four unknowns, so we don't have enough equations. We have four unknowns and three equations. So what do we do about that? Something for you to note is that when you are doing these equations right here, there is a force that's a frictional force, just so you know from here, coming from here, in case you haven't noticed. So if we have three equations and four unknowns, we need to build a fourth equation. And like I said, this is not the case all the time. Sometimes we're doing exercises in which it's very clear that the disk is rotating, and when that's the case, then we don't have a fourth unknown. The problem will be very easy for us to solve. But anyways, if we have four knowns with three equations, then we need to study two possible cases. The first case is assuming that no slipping it's happening, and if that's the case, then the acceleration will be equals to alpha, or angular acceleration, times the radius, and that will be the fourth equation. We do not use this one if that's the case, and after solving, you will need to verify that the frictional force is actually, smaller than mu s times the normal. If that's the case, and your assumption was right, and then you can move on. And then if you assume, but you usually assume this one first, and if that is not, if the assumption is not verified, then you have to go to case number two, which is assuming a slipping, and use the equation as a frictional force equals to mu k times the normal. And if that's the case, basically you're just saying that there's no alpha in the equation. So the procedure for analysis is very easy and standard. At first you have to establish XY coordinate system. We always do that, and then after that you need to draw both the free body diagram and the kinetic diagram for the body. Then you have to specify direction and sense of the acceleration of the mass center. Okay, that's very important, and the angular acceleration of the body. If necessary, compute the body's mass inertia, mass moment of inertia. If you're given with that, you could be given with a table, a certain shape, or you might have a radius of gyration. What matters is that you have that number, so you can simplify your calculations. If the moment equation, it's this one, the one that you're using, then use the kinematic diagram to visualize the moments developed by the components. You will have multiple forces. Each one of those forces, if they have a distance, they will cause a moment. It's very important that you know that, so you can put all of those terms into that equation. And then obviously don't forget that the mass moment of inertia times the alpha is the torque that this is causing into the whole system. Then we have to apply the three equations of motion. We need to identify the unknowns, and then, like I said, if you have more unknowns than equation, then you have to use kinematic equations to, if they're necessary to complete the solution. Then after that, if you still have, more unknowns than equations, then you need to apply the two cases that I explained in the previous slide. If no sleeping is happening, or if it's happening, then, solve for unknowns, and you should be fine after that. And again, let's just do an exercise to visualize everything that we have talked about. All right, so spool has a mass of 200 kilograms and a radius of gyration equals to zero point 0.3 meters. The coefficient of kinetic friction between the spool and the ground is 0.1. Mu k is given, so we need to find the angular acceleration of the spool and the tension in the cable. So the plan is to focus on the spool, follow the solution procedure, and identify the unknown. What is important here is that we read what it's given. We kind of can start using the procedure, but we were given with a radius of gyration, which is something that has to tell you, like, okay, what is this gyro of gyration? Is a resistant to angular acceleration. So there is angular acceleration involved in this problem. And then if there is an angular acceleration, then this is rotating, and the movement is very clear. As this is rotated into this direction, then it's moving towards that direction. And if you have that clear, then you might be able to simplify your equations, because you will be able to then give a value for the acceleration of the center of mass equals to, mass times alpha. So the free body diagram and kinetic diagram are given like this. We need to calculate the tension. So we have the tension right here. It's moving into this direction, or it's rotating. And as a result of that, the whole thing is moving like this. There is an IG involved. We have, weight, and we also have, the frictional force right here. All we have to do is just start doing the sum of forces, right? The first thing will be obviously the sum of forces into the y direction because that will make sense just for us to get the first unknown. So sum of forces into the y direction, and this is positive for me, will be equals to 0, obviously, because there's no movement in the y direction. And if that's the case, then I have MB, minus the weight, which is 1962, and that equals 0. So therefore, MB will be equals to 1962 newtons. So finally, I got my first unknown, and now I will sum of forces into the x direction, and that's equals to mass times acceleration in the x, which is the only acceleration that we have present right here. So we have the tension, and this is positive for me. So if that's positive, then we have the tension minus the frictional force, which is 0.1 times MB, which is 1962. We just solved that, and then that will equals 200 times AG. Okay, and that would be my first equation. And then if I do then sum of moment around G, that will be equals to IG times alpha. And this is something very important because IG, how do we find IG? We were given with radius of gyration. And if you remember our previous video, you might know that mass moment of inertia is also equals to the mass times the radius of gyration to the square. So if you use this equation, you can easily find this because I will be equals to the mass, which is 200, that multiplies 0.3, which is the radius of gyration that was given to us. And therefore, you don't have to find a table. You don't have to do anything like that. If you know the knowledge, then you can use it in your advantage. This is another example on how important it is to know everything. And if you don't remember what the radius of gyration is, then just go back to the previous video. You will be able to find that over there. 450, which is the couple moment, minus the tensional force that multiplies the distance, which is 0.4, right? Yes, it is. Yeah, 0.4. It's right here. And then I also have minus 0.1 that multiplies MB, which is 1962. And then that also it's been multiplied by 0.6. It's right here, the frictional force that is causing the torque. And then that is equals to 200. That is when multiplied to the radius of gyration, which is 0.3 to the square. It's right here, remember? And then this is also being multiplied by alpha, right? If I'm not mistaken, yes. So now I have a second equation. And what we need to realize here is that we have one unknown, another one, and we also have alpha. So we have two equations and a third unknown. But in this particular case, we know that there is rotation involved because of this, the radius of gyration. So clearly AG, right? AG will be equals to alpha R. I can perfectly use this equation because there is happening rotation and therefore I don't have to do any assumption, and that will be my third equation because the radius is it's clearly given, so this will be 0.4 since I'm just concentrating on the spool. Alpha, by solving those equations, I will get that alpha it's equals to 507 radians per second square, and then the tension that needed to be calculated is 602, 28, and that's newtons. And now I just solved the exercise. So the important thing behind this problem is that we were able to start looking at the data that was given and apply the equations properly in order to get to our final answer. That's why I didn't have to make an assumption. The movement was very clear and specified by the different data that was giving, and that was it. I was able to solve the exercise. Obviously, if you have questions, like I said, you're more than welcome to email me and I will help you understand these kind of exercises. They're not hard. This is actually the easiest part of the whole chapter. All right, guys, with that, we have completed chapter number 17. I want to thank you all for watching my videos. This is very cool when I see, that you leave a like or a comment. That's very rewarding for me, and that's why I do all these videos, not only for my MCC students, but everybody out there. All right, thank you very much for watching, and I will see you in the next video.